Can you see my slides?
Yes.
Okay. So let's talk about convolutions over volumes. The idea is that the input is typically a volume, not a flat or a one-dimensional image. So you have 3 dimensions at least, which is the RGB. Yeah, because we're talking about computer vision here, right? So you have the height, the width, and the depth is typically 3 because of a given input. Okay, so let's say I apply a filter over this this image, which has right 3 channels, the R, the G, and the B. I apply a filter that is also a cube, a volume, not a one-dimensional filter. So what we're looking at before was just one-dimensional. I have right a single dimension, and I'm applying a single dimensional filter. Now I'll apply a volumetric filter. Yeah, so which is equal to the same size as the input. So the filter volume or depth is equal to the same depth of the input. So I have here 32 by 32 by 3 image. I apply a filter of 5 by 5 by 3. Okay, so it's always filter always extend to the full depth of the input volume. And how does it work? It really works the same way as before. So it's a set of weights. Now you'd have 5 by 5 by 3 weights. And these guys are multiplied by the pixel values of part of the image. So here, right, this is the part I'm looking at. So I'm applying the filter, I'm moving the filter across the image, and this comes, right? So this is one neuron or one activation. Basically, it's just the sum of weights, weight times pixel value, weight times pixel value, weight times pixel value, done across the different volumes or different depths. Okay. So basically, the result is what? The result is 75-dimensional dot product. Why 75-dimensional dot product? Because you have 5 by 5 by 3. That's the number of weights. That's 25 times 3, 75 times 75 pixels. Yeah, that gives you a 75-dimensional dot product plus the bias, of course. Yeah, you have the WC. Okay, so the idea is just extended this over volumes. Okay. And that gives me what? The result is the output is an activation map. So it's here a 28 by 28 by 1. So the depth is 1. Why the depth is 1? Because I take the volume and I do write a filter over it or a convolution over it, and that gives me a single number. So I end up with a one-dimensional output. So that's one activation map. Why the size is 28 by 28? Because I have 32 minus 5 plus 1. Assuming that the stride and the padding is 0 and the stride is 1. So I get 32 minus 5, that's 27 plus 1, that's 28. So I get 28 by 28 by 1. Okay, now I can apply another filter. So basically a new set of weights, 75 weights or 76 weights to be exact, the green one, and that gives me another activation map. And I can apply multiple activation maps. So what happens typically in convolutional neural networks is you apply multiple filters, each one sharing the same set of parameters or having the same set of parameters, and then you apply multiple of these. Let's say 6 5 by 5 filters. That will result in 6 28 by 28 activation maps. Yeah, so you get a new image of size 28 by 28 by 6. Pixels if you wish. Understood? Okay. Why the output size? Again, 28 by 28 is 32 minus 5 plus 1, right? Because the padding is 0 and the stride is 1. So we get 32 minus 5, size of the filter, plus 1, and 32 minus 5 plus 1, which is 28 by 28. And I have 6 of these filters. These would result in 6 28 by 28 images if you wish. Okay. How many parameters do I have? Total? Any thoughts? Each one 5 by 5 filter is how many parameters?
6.
75 by 6, you said?
25 by 6.
25 by 6 is correct, except that it's volume, the volume. Don't forget the volume, right? So here, I have the filter goes over the volume. So it's 25 by 3. So it's 6 by 25 by 3, because the input size is of depth 3. So it's 6 times 75, not 6 times 25.
Okay.
Got it?
Yes.
Okay. So 5 by 5 by 6 by 3. Don't forget the 3, which is the depth of the. Okay. That's pretty much it. If you understood this, you would understand convolutional neural networks and you will be able to train them. Because training them is similar to training a regular neural network, right? Backpropagation, nothing else. But it's the architecture itself. How do I set up the architecture is really what we're talking about right now. So a CNN is a sequence of convolutional layers intercepted with activation functions, typically ReLU. So what you do is you have an input image, which is typically of depth 3, and some, height and width. So some number of pixels for height and width. You apply a convolutional layer. What is a convolutional layer? A set of filters, for example, 6, 5 by 5 by 3 filters. Why 3? Because the input depth is 3. So it's exactly the same as the input depth. That becomes, it gives you a set of activation maps. You pass these through non-linearity. So typically a ReLU, a rectified linear unit. And that gives you the input to the next convolutional layer, the next hidden layer, if you wish, which is now 6, 28 by 28. You can apply 10, 5 by 5 by 6 filters. Why 6 filters? Because it has to be the same depth as the input. So that gives you, right? And then you pass this by the some nonlinearity. Yes, depth 3 for RGP, yes. And then you got an output which is 6, right? Because you concatenated the different maps. And so that's why I use the filter. Next filter would be of depth 6. Right? So 5 by 5 by 6 filters, 10 of them. That gives me a depth of 10 because I have 10 filters. And the height and width is 24 because I can apply the formula. Look at 28 minus 5 plus 1. So 28 minus 5 is 23, plus 1 is 24. They pass this through some nonlinearity. So every pixel passes through some nonlinearity, typically ReLU, and that gives me the input to the next layer. Let's see the ReLU activation. So let's assume this is the input, right? So this is the output of the convolution operations. And if I apply ReLU on it, why do I get this? Who remembers what ReLU is?
The negative values become 0.
Exactly. And the positive values get output as is, right?
Yes.
Okay. So let's apply ReLU. This is the result of an activation map. And then we apply ReLU to it. 9 is positive, it gets output as is. 3 is positive, it gets output as is. 5 is positive, it gets output as is. And minus 8 becomes 0. The minus 6 becomes 0. 2 is 2. Minus 3 is 0, and so on. So that's what it means by applying some nonlinearity or a ReLU activation over some activation. Okay? All right. Hence the name activation map, because I apply some nonlinearity over it. So, summary of convolution layers. In a convolution layer L, so let's say I have a layer L, the input size is going to be n height times n weight times n depth of the previous layer. So it's coming from the previous layer. For instance, if it's the input layer, it will be 7, or like let's say 32 by 32 by 3, because you have RGB. Yeah, and then the next layer, depending on the number of filters you're using, this ND would be set. So if you're using 6 filters, this ND would be 6. Okay, so that's the input from the previous layer. And the output size is going to be n height of L, and width of L, and depth of L. Okay. I have KL filters that I'm applying in this layer. Each of has a size, a width of FL, a height of FL, and a depth equal to the input size. Remember that the depth of the filter is equal to the depth of the input image, yeah, or input, the input sample, yeah. So ND of L minus 1. Okay. I have a stride of S of L. I have a padding of P of L. Okay. Let's see the output size. So NH of L would be basically based on our formula, the input, the height of the input time plus 2P of L, the padding, minus F of L over the stride plus 1. Same thing for the width. Who can tell me the depth? What is ND of L is equal to what? Any thoughts? I'm using KL filters. It would be equal to K, right? K of L. Because you apply every filter results in one activation map. So I get a depth at the end equal to the number of filters that I apply. I have 4 hyperparameters per layer in a convolutional neural network. The number of filters, the size of the filter, F of L, the size of the stride, and the pad. So these are the 4 hyperparameters. How do I set these hyperparameters?
Validation.
By validation. What's that? Somebody said something.
في حدا عم بيحكي مع بيو.
مع بيو. Okay. Right. So I do validation. Type the number of learnable parameters. Anybody can tell me? So these are the hyperparameters, but what are the weights? Number of weights per layer. How many weights are there?
شو هو ال NW؟
The W.
Size of the filter.
It has something to do with the filter. So it's basically how many FL by FL by ND of L minus 1 times KL. What's that?
You lagged. Can you repeat that?
Yes. So the number of weights, the number of learnable parameters, right? The number of learnable parameters is FL times FL times ND of L minus 1. That's per, filter, because the filter has a volume. You get this is the number of weights that you need to learn. How many filters do I have per layer? I have K of L. So that's equal to the number of learnable parameters. The plus 1 here is for the bias. Yeah, because per filter, I have a 1 bias.
Yes.
Okay, good.
Yes, sir. I have a question.
Sure.
If we to set these parameters by validation, and the neural network is like 100 layers, it will take a lot of time. So can't we do something about it?
So typically, no, right? So the more hyperparameters you add, the more deep the neural network is, the more time it will take to train. So it's typical, for instance, for these very deep neural networks that you can train them for even a month. Yeah. So this is something that that is common, right? You would leave it training for a month. In practice, most of the people avoid using deep neural networks. If you're gonna train the whole network from scratch, you avoid using like a deep neural network. But there is something called transfer learning, which we're gonna learn about in a bit, like in maybe a couple of lectures. And the idea is to learn only the final layers, to train the final layers of the network. So use a deep neural network, but use pre-trained weights. So it's fix the weights of most of the hidden layers and just train the final layers of the network. Yeah. So that adds a lot of efficiency to the training of a neural network. Okay.
But they're not as the results are not as accurate as training the whole neural network stuff.
Surprisingly, most of the cases, because you have limited training data, so it acts kind of a regularization. Yeah, you're not learning all the weights, you're fixing some of the weights. In practice, it works pretty well, particularly if you transfer the weights from a very similar task to the task you're training on.
Okay, sir. Thank you.
Okay. So summary of convolutional layers, right? The typical settings, and these are the ones you're gonna, when you do the assignment or when you do projects, usually k is the power of 2, so example 32, 64, 128, and so on. F is 3, S is 1, P is 1, that's a common, right? So the filters are typically small in size. You don't do, right, large filters, so 3 or 5 or 7. You know, strides, you can try 1 or 2. You can try padding of 1, padding of 2. Yeah, so you have some, you know, very small set of values that you could try, and you set this using parameter tuning, hyperparameter tuning, using validation. Yeah, but there is not a lot of you should not try a lot of values. There is, you know, predefined values that typically work in practice. Yeah, and there are default values when you're training at convolutional networks. You can start with the default values and then change this to see how the performance is affected. Okay. So at the output side, the input side 32 by 32 by 3, and you're using a 10 5 by 5 filters with stride of 1 and a padding of 2. Just a reminder of what we're doing.
We will get back to the last slide to calculate each one of them.
So
As we know that the last one would be 10.
But, so you have 10, that's the depths of the output, and then you have 32 plus a padding of 4, so 32 plus 4 minus filter is 5, so 32 plus 4 is 36, minus 5 is 31, plus 1 over 2 plus 1, right? So 32 plus 4, 36, minus 5.
But S is 1, sir. S is 1.
Stride of 1, right? So it's basically 32 plus 4 for the padding over 1, which is 32 plus 4, that's 36 minus 5 is 31 plus 1 is 32. So you get 32 by 32 by 10, as you said. Why 10? Because I'm using 10. Okay?
Yes.
Perfect. Finally, we do something called pooling layers. So in every convolutional neural network, typically do something called pooling. I'll try to summarize all of this at the end and give you some, you know, hints on how do I use it in practice. And then you will see, of course, with Shadi, how do I train one using Keras, for instance. Okay, so I typically do something called maximum pooling after a convolutional layer. So what's a maximum pooling operation? It has, you apply a filter, right? Typically, let's say 2 by 2 filter. So I have here a 4 by 4 image. I can apply 2 by 2 filter with a stride of 2, and it does maximum pooling. So it goes over the 4 pixels and picks the maximum value for it. So here I have 1, 1, 5, 6. It takes me 6. What is the maximum value of all these 4? It's 6. And then I do a stride of 2. So I go to the next 4 pixels, 2, 7, 4, and 8. What is the maximum value? It's 8. So I output 8. 3, 2, 2, 2, 1. I output 3. And 1, 0, 3, 4. I output 4. So this is called maximum pool. Yeah. And it works. It's a filter, but there are no weights here. You're just doing a maximum operation. So what is the use of it? It makes the presentation smaller, and more manageable. So it kind of gives you a chance to shrink the images after a few convolutional layers. Yeah, so you use it as a shrinking method to reduce the number of weights that you have, but not after, right? I think after every layer, after few layers. Yeah. It operates over each map independently. So it takes, for every map, you do maximum pooling. Yeah, it's not that it works on the whole volume, it works for every map independently. So I have 2 by 2, for example, the input is 2, 2, 4 by 2, 2, 4 by 64. If I do maximum pooling, I end up with half of the image almost. 112 by 112 by 64. Why by 64? Because it acts over every map independently. And why is 112 by 112? Because I'm assuming I'm using a 2 by 2 like maximum pooling filter with a stride of 2. Yeah, so it does a downsampling. You take the image like this, you downsample it into half the size, for instance. Okay. Why 0 learnable parameters? How many parameters does it involve, this pooling operation? Does it involve any weights? No, it doesn't involve any weights. You're doing maximum over the values of the pixels. So it doesn't involve any weights, hence it's 0 learnable parameters. And 2 hyperparameters, the filter size and the stride. Only 2 hyperparameters. Okay? So let's see a summary of the pooling layers. The input size in a layer L is going to be the height from the previous layer, the width from the previous layer, the depth from the previous layer. The output size is the current height, the current width, and the current depth. And let's say I'm using a pooling filter of size FL by FL. Here there is no depth because I'm doing it per activation. I have a stride and I have a path. Okay. The output size NH of L is going to be using the formula as before. The width is going to be using the formula as before because I'm doing, you know, one value per the set of pixels the filter is passing over. Okay, and then the depth of the pooling layer is going to be the depth of the previous layer, because it's applied on every activation map independently. I have 4 hyperparameters: the filter size, the stride, the pooling, and the type of pooling, whether I'm doing maximum or I'm doing average instead of maximum. In practice, maximum works best. So most of the people use maximum pooling rather than average. Here are typical settings for a pooling layer. You have the filter equal to 2, the stride is equal to 2, or the filter is equal to 3 and the stride is equal to 2. Use typically 0 padding, y is equal to 0, and typically use maximum pooling as I just. And then the number of learnable parameters per pooling layer, again, remember it's equal to 0 because I'm not learning any weights. There are no weights to learn. I'm just applying either average over the pixel values or maximum over the pixel values to downscale them. Towards convolutional neural network, it's a series of convolutional layers followed by activation functions, typically ReLU, and then pooling layers, and then ending with fully connected layers. So the input is an image. Let's say we want to classify, our goal is to classify whether an image is an image of a car, truck, aeroplane, a ship, or a horse. Yeah. So I take the image, pass it through a convolutional layer, which detects some edges. So one would detect, you know, horizontal edges. One would detect vertical edges, and so on. Pass after the convolutional layer, you pass an activation layer, so ReLUs. Then you pass the output to a convolutional layer. Then you pass it to a ReLU. Then you pass it to a pooling. And you see pooling is not done every layer, right? Because you don't want to downscale the image aggressively. Yeah, you want to downscale it every few layers. Yeah, so then you can do one layer of pooling, then some convolutions, then some ReLU, convolution, and so on, right? And then finally, you get at the end, right, some pooling layer that gives you some downscaled images. Now you can pass these downscaled images to a set of fully connected layers, typically 2 or 3, and then use a softmax if you're doing multi-class classification. Yeah, so this is a typical architecture for a convolutional neural network. Yeah, you take the image, pass it through some computational layers, some activation, some pooling, and then at the end, some fully connected layers, and then softmax if you're doing multi-class classification, or basically logistic regression, so sigmoid if you're doing binary classification. Okay, so CNNs generalize well. Why is it very powerful now in computer vision? Is because of parameter sharing. So you have a lot of parameters that you're sharing in the computational layers. You don't have any parameters in the pooling layer, so you reduce the number of parameters drastically, and you also have sparsity of connection. So you don't have, you know, that not the whole image is connected to every neuron in the neural network. Okay, so that's really ends convolutional neural networks. Next time talk about more architecture. So really practical architectures you see in libraries and you could use off the shelf. But the idea is as follows, right? When you're training a new convolutional neural network, this is what you have to set. You have to set, the layers, like you do in neural network, number of layers. You will say, okay, the first layer is a convolutional layer followed by, an activation layer, and then I'm gonna do maximum pooling or not, and then you pass it to the next layer, and so on. You have to specify the number of filters per layer, the size of the filter, stride and padding, and set these hyperparameters using some validation strategy. Yeah, this is more or less what convolutional neural networks are. Okay, let's talk about, if you have no questions.
So will we have an assignment for this?
You'd have an assignment for this. It's going to be really cool. So with some images, and you will try the classifier for them. Speaking of assignments, you still want an extension? I know Shady give you like a...
Using Keras also, right?
Using Keras, yes. You're going to be using Keras for that. So from now on, we're going to be using Keras for the rest of the of deep neural networks, at least.
Sir, but Shadi told us that Keras is not like PyTorch is better because like we can manually set the learning.
Yeah, so PyTorch,
something like that.
You recommend it once you're more comfortable with neural networks because you can actually play a lot with the architectures. You can change them. And so on. So Keras is like an interface on top of TensorFlow. So it's usually easier to start with Keras, but then once you're more comfortable, you can just go directly to TensorFlows and you can change everything: the architecture, the learning algorithm, backpropagation. You can play with it and so on. Yeah, but it's recommended to start with Keras because it's easier as a library to use. But feel comfortable to go directly to TensorFlow if you want. Do you still want an extension after the training yesterday?
Okay, thank you.
Do you still want an extension on the assignment, or you're fine with it now?
Yes, we still want the extension.
Okay. طيب, we'll extend it.
المواد الأحد.
نعم.
هو الديدلاين الأحد؟
الأحد. Yes, Sunday.
I think that we can make it on Thursday instead of Al-Ahad. I know we still have previous assignments or exams next week.
I'll extend it a little.
Start with Thursday, like it's too much, but
Now?
more days is better.
Thursday too much.
And like any day, no, it doesn't have to be Thursday like that much, but like at least 2 days so we can.
Okay, let's do it Tuesday.
We have,
right, you can also submit later if you can, right? If you can manage, right? But I want you to do. I mean, it's really important for me that you guys start doing training neural networks right now because of the projects. It's mainly for the projects, whether FIP or the projects of the course. Yeah, I'm assuming most of you are going to be using neural networks, and so it's really a good time for you to start getting comfortable with training neural networks. Yeah. The sooner the better.
Sir?
Yes.
Even if you extend the assignment, can you still post the next assignment on Sunday just so we can look at it?
Yeah, sure. We'll do that. That's fine. Okay,
Thank you.
You're welcome. Other things? Okay, folks, then we'll talk on
Any news on the exam?
and use our exam. So as I said, don't worry about it. We'll fix we'll fix the percentage of it. So I'm not gonna put a lot of weight on it. If you're doing well in the other parts, I'm gonna take this into consideration. Yeah, so you don't have to worry too much about it. Okay.
sir, I talked to you 2 days ago by email about office hours, but today I think you didn't have.
Yeah, I have a talk that I have to attend. You can talk to me after on WebEx, yeah? So you have my WebEx room.
So what?
Sir,
You can't today?
I can't. I didn't hear what you said.
So you can
I didn't hear what you said. متقطش.
Yeah, so you can talk to me after the class using WebEx. You have my WebEx link, right? So just log into WebEx and I'll be online and consult there. Okay?
Okay. Thank you.
Any other questions?
سير اذا عملنا منيح بالاكزام بضلوا الويت عليه نفس الشيء ما هيك؟
I'm gonna like I'll look into changing the weight of the exam. Yeah, so I'm not. يعني the average is really low, so it will.
قصدي اذا عملنا منيح بالاكزام.
Okay, changing the weights, شوي magic.
نعم.
Do your thing يعني بروفيسور لأنه نحن حرام.
Yeah, I will.
سير
It's
قصدي اذا
gonna be
عملت
fine يا رحال.
ده اللي عمله منيح بالاكزام في يضلوا الويت مثل ما هو؟
Yeah. So I'll try to look at every case individually. Yeah.
اوكي يا ذاتس وات اي مانت لحتى ما حدا ينظلم حتى اللي عمله منيح او مش منيح.
اوكي بس
الافريج 55 وما شفت حدا جاب اعلى من 70 بصراحه.
في 80.
انا
بلا في ناس
شيء
عملت
بفضل تبقى صراحه.
في
بروفيسور قديش اعلى علينا؟
80 something يا محمد. There are people who got in the 80s, yeah.
بروفيسور ما سمعت شو قلت عن الاوفيس اورز.
So please, you can log in على WebEx. You know WebEx, my WebEx room. You will find me there after the class. So you can just log in and we talk. Yeah.
Deal. Where can you find the link of the WebEx room?
تلاقيني بعتها by email.
Was it the one for the midterm, the same link?
Yeah. The same one for the midterm.
The one of the midterm? Deal.
Okay. All right.
Okay.
Yalla. See you guys.
Okay, thank you, Professor. Bye.